Share my screen. There we go. Today, we're going to finish up talking about PageRank stuff. Before we do that, though, and again, if you don't have the notes, there's a notes packet in the front corner over there. Before we go over PageRank, quick announcement about the midterm. All the details posted as a new issue to GitHub. I just did it like 30 seconds ago, so you'll get an email about it next time you check your email. But the days that I've chosen to do it from, Thursday, September 22nd, so about 10 days from now until the following Sunday. So 4 days or so to work on it. Hopefully that's long enough that somewhere in there,
recording in progress
for yourself, and it's not going to be like overlapping with class sessions or anything, so we don't have to feel awkward about not talking about it during the middle of class. Format, there'll be 15 points, 15 problems. 10 of those will be true false style problems. The very last page in the notes packet has some examples of those. We'll get to those, how to think through those today. And then 5 free response questions, where those 5 questions will come from just other portions of the different packets of notes, doing something very, very similar to what those other things are doing. So if you can do this thing, all the problems in the notes, then you'll do excellent on the midterm. Yeah, I don't plan on going over the rest of these right now. I'll talk about it actually a little bit before going over giving you the midterm, but basically fully open note, open book, open computer, whatever you want to use. Any administrative questions about this or about anything else before we get started on material stuff? Programming projects due this coming Sunday, so you'll be able to get that totally out of the way before the midterm. And again, so the due date is this Sunday, and the if you collaborate with other people in any form, working with other people in the class, I strongly encourage you to do that. Then you'll get a 48-hour extension until next Tuesday at midnight. Any questions about the homework project? How many people started? Okay. Totally okay if you haven't. Assuming things go well for you and you can figure out how to get everything to run and stuff, then I don't think it should be a hard assignment, but that's assuming everything goes well, which it probably won't because it never does. But okay, yeah, so today we'll be talking about finishing up our PageRank notes, the last of the material for this, and then totally new material starting next week, where we'll be going to that textbook that I gave you all at the beginning of the semester. So here starts a little bit, I don't know, less technical, motivation-y, background-ish knowledge. Some more examples of when you might want to use PageRank. So maybe like reading that deeper inside PageRank paper, like, okay, this is cool, but I don't really care about the internet. I'm not going to make a Google competitor. How might I actually care about PageRank? And so I want to talk about some of these examples, or some more examples. So this first one right here, if you imagine you're in charge of advertising, like at Apple, whatever big company that's just created this new iGadget, and you want to deliver free samples to Twitter influencers. Could be any other social network too, but just picking Twitter. And the idea is that they will write great reviews of your product, and lots of other people will see it and buy it because of that. And so how do we decide which people we should give the free samples to? One idea you might have, and this is a bad idea. The bad idea is let's look at who has the most followers on Twitter. Who has the most followers. And give our iGadgets to whoever on Twitter has the most followers. So my question is, why is this a bad idea? If our goal is to get the iGadget into people who are going to be able to talk about it in front of a lot of people, why is giving it to people? Yeah. Go ahead. Okay, yeah, so one problem is maybe it's not specific about like which followers. Like maybe if we're advertising a technical product, giving like Trump has a lot of followers, but that's not his audience. Other reasons, yeah.
People can have lots of followers, but not a lot of people like people won't engage with them.
Okay, a lot of followers, but people don't engage with the tweets. Maybe I'll say that followers not a good measure of engagement, rewording it that way. And in particular, like how might that happen? Well, the common thing people talk about all the time on social media, especially Twitter right now, is bots on Twitter or fake accounts that are just like following people, but they're not actually, there's no person behind them. So bots or other low quality accounts. And so somehow, really what we want to do, we're trying to find these high quality accounts. And we have various reasons why this is not a good measure of quality. So let's use PageRank as our measure of quality. In order to use PageRank, we have to sort of formalize things as a graph, because PageRank is over graph, finding the most important nodes in the graph. So here are the nodes in the graph. And this will be our good idea. The nodes in the graph will be all the accounts, or the people, the user accounts. And we'll have an edge from A to B if A is followed by B. And this followed by right here, it's important that this direction is correct, that you'll get the opposite results if you had the arrows flipped. But here, so if we had like, just drawing out an example here, mentioned Trump already, if this is his account, he doesn't follow a lot of people, but he has a lot of other people following him. So there would be a lot of arrows coming out of his account into other accounts. If we were to use PageRank on this graph, it would give us a generic picture of who is the most important person or people on Twitter ranked by their importance, not taking into account like the fact that we're looking maybe at technical people. Like Trump would still have a very high PageRank according to this graph. And if we made one more sort of modification, if we set our personalization vector so that techie people, whatever that means to us, and doesn't have to be all the techie people, but some subset of techie people have high values and everyone else small values, then that's going to cause us to be specific about who we want to be our ranked high. And so in that case, Trump would not get ranked high. And I know all the techie people that I can think of are like Linuxy sort of people, probably not super interested in iGadget stuff. So maybe you want, I don't even know if Linus has a Linus Torvalds or Guido von Rossum, any of those people have Twitter accounts. But if they did, then maybe they're sort of people who you want to have high page rank. So you set their personalization vectors high, and then all the people that they follow will get influenced. Any questions about, yes?
So the key difference between these two is the personalization vector, or because with using PageRank, the bottom one, like when we set it as like you have a node, whether if someone's following them, wouldn't that just prefer the person who's most followed?
Yeah, so I guess I have 3 ideas listed here of just doing the page rank to get filter out who's like just as the measure of engagement. And then you could also add the personalization vector to get more specific, filter out specific people.
Sure, but like if you just did PageRank with like who's following who, how would that be different than looking at who has the most followers?
So the question is, how is PageRank with who's following who different than who has the most followers? And this goes back to the first problem on the previous notes where we saw that the in degree of a graph doesn't actually have any necessary correlation with the PageRank. That if you're just to randomly generate a graph, or if you generated a graph that you thought was reasonable, it would probably be the case that the in degree and the PageRank are very correlated. But in the worst case scenario, the highest PageRank thing can have an arbitrary small in degree. And we saw, so this is just repeating the graph from the last set of notes that looked something like, have a bunch of things going into this. So this has a high in degree and a high PageRank, but then that is referencing something else. So maybe if everybody over here is yeah, everybody over here is following Trump, and then Trump is following, I don't know who Trump follows, but somebody else, then that other person is also going to have a high page rank, even if Trump's the only person who follows them. So no necessary like correlation between the in degree and the page rank. Yeah. Yeah, good question. The question is, why did we choose to have the edges go the direction that we chose? And let's see. So in the statement right here, from A to B, if A is followed by B. So we want Trump to be followed by many other people. So if A, I think I said that backwards because we want many arrows going into the important people, the people that are being followed many times. So many arrows going into Trump. That way the page rank flows into the Trump node. And so if this is A and this is B, we want an edge from A to B if A follows B. Apologize for that. Thank you for the correction. Yeah, and so the in degree now of Trump also high because the page rank is also high. Paul. X out that. Good questions. The next example is a rather different one, not one that people talk about as much as like so this graph right here is sometimes called the social graph when people are talking about Twitter, Facebook, Instagram, all these different things. And usually people talk about it in the context of advertising because there's a whole bunch of money in it. But military sort of people also talk about killing people, and they use PageRank for that. So if you are the director of the CIA and you want to kill terrorists, what is a way to identify likely terrorists? If you are one of the ROTC candidates who are just below us right now, what is the way that they're being their orders are being chosen? It's all using PageRank. So in this case, the nodes would be all people on Earth. The edges somehow representing that two people have contact with each other. Common way of doing that is using phone records so that two people have an edge between them if there's a phone call. And you can make it a unidirectional or a bidirectional edge. I'll write bidirectional. Bidirectional edge if person A and B talk on the phone. And something like this by itself would give you all of the people on the Earth who are the most sort of important people. If you have an idea and that idea spreads through the phone network, who are the people who are most contagious with their ideas. But then if you add that personalization vector, I'll write it this way, VI is large if I is a known terrorist. Otherwise, it's small. Then now it's the ideas are somehow focused on like terrorist-ish ideas and who are spreading terrorist sort of ideas to each other. I have a little graph that I want to draw about this. Try to keep it all on the same page, all on the screen. And so if we have these three people right here, and I'll color them in because we're going to say somehow we know that those people are in fact terrorists. And some more people up here. Just draw lines between them for edges. This person talks to a lot of people. This person also talks to a lot of different people. Down here, edges to like these people. And did not want that edge right there, or that edge right there. Make this edge go all the way. Add something like that. Now for computing the PageRank, where again, so like the idea of this personalization vector is that if you're thinking about it as the random walk, then whenever you do that sort of teleporting phase, decide to leave whatever node you're on, you're going to teleport back to one of these vectors, one of these nodes right here. And when we do that, we'll be bouncing around over here between coming to these nodes over here quite a bit. And whatever other nodes are off on this graph, way over here, far away from the terrorists, we're basically never going to, or very, very rarely get to them because they're far away from all of these. If we were just looking at like who are the immediate people who talk to terrorists, then we would identify like these people up here and these people down here, all the people who just immediately talk to them. But maybe this is like, I don't know, a call center like the AT&T helpline. And so lots of people talk to the AT&T helpline. Just because a terrorist talks to them doesn't mean that like they facilitated terrorism anyway. Or yeah, just because a terrorist happens to call you doesn't mean you're facilitating terrorism. It's just if lots of terrorists talk to you or you talk to lots of people who also talk to terrorists. So the PageRank will assign high PageRank to the orange things, that, and that would have high PageRank. This one in particular never actually talked to any of the known terrorists, but it's still going to have a relatively high PageRank. This stuff up here, it's going to have all very low PageRank. Leave this up for another minute or two. But I'm going to switch the screens here in a second to a video of former director of the NSA and the CIA and a whole bunch of other security agencies, Air Force General, 4-star General. His name's Michael Hayden. Here's a picture of him. There's Michael Hayden. His Wikipedia is just full of all sorts of security related things. And watch the video on the computer so that the sound goes. And he's just going to, he's not going to use the word PageRank, but he'll tell us how he uses this stuff to kill people.
You can find out all these things David just said about me, about David,
So
and this audience.
This guy over on the right is the general.
That is a function of operational capability. I'd like you to talk about whether you're comfortable with that operational capability. If so, why? And how often is it used in the ways that David described?
Yeah, first of all, David's description of what you can do with metadata, according to mutual friends, is absolutely correct. We kill people based on metadata.
So when he's saying that, he's literally meaning that like PageRank is what he's using here. These edges. Oops, that's not it. These edges, like who has talked to who, that is the metadata. NSA doesn't actually care about like what you're saying to people. They just care about who you're talking to, and they use that to come up with this list of targets and decide which missiles, what GPS coordinates to send their missiles to kill people. If you're interested in more of those details, that link down at the bottom talks more in detail about that. Any questions about any of those? Just examples? The big picture takeaway is that if you can somehow like think about whatever problem you're working on as a graph where you're trying to come up with like what is the most important node in that graph, then PageRank is going to be a good tool to use that on. Okay, skip number 2, let you do that on your own and come to problem number 3. Getting into more runtime technical details. Last time, we talked about the power method. So the power method is, again, the standard method for computing PageRank. It's what everybody uses in practice. And it's what that Deeper Inside PageRank paper goes over. This problem number 3 here is going to go over an alternative algorithm, an algorithm which I call the exponentially, oh, why did you jump? This exponentially accelerated power method. And we'll see that in certain situations, this new algorithm will be faster than the power method, and in the vast majority of situations, the standard power method will be faster than this method. There's a lot of text here. I will explain what's going on, and then we'll get to the actual problems. So the standard power method, the main thing is this equation 1 right here. And this is again in the PDF file, equation 5.1. It's what you're implementing in your programming project, and it's what we talked about in length last time, analyzing the runtime of the power method. And what I want us to recognize is that this is a recursive formula. So we have x to the k. That's not like an x raised to the k power. You can't raise a vector to a power. That doesn't make sense. So this superscript k up here indicates that it's like the version k of x. And that's based on version k minus 1. And so if you sort of unravel that recursion, make it more iterative, describe it in an iterative way, then you get this equation 2 down here, which is not stated anywhere in the PDF, but it's 100% equivalent. And in some sense, it's not stated because this is the, again, to use that obnoxiously mathematical word, should be obvious. Although obvious means that it might take you 20 minutes to figure out. And then the key thing here is that this p to the k is a bunch of matrix multiplications. And we've been talking about runtimes of matrix multiplications. And one of the things that we talked about is that the order that you do those matrix multiplications in matters. So we have a big white spot down here. I'm gonna draw some stuff. And this x to the p bar to the k, so that's that same just formula right here. That's what the xk is equal to. If instead of writing out p to the k, that's just x p bar times p bar times p bar, and so on. And just k times. Work that out. And now the key idea is that, again, matrix multiplication is not commutative, but it is associative. So I can put parentheses in here however I want. What the power method was doing is that it was putting parentheses like this. X times p bar. You first do that. And we call that the x1 like that. And then you multiply that result by p bar again, calling that whole thing x2. Multiply that whole result by p bar again, calling that x3, and so on, doing one matrix multiplication at a time, just going from left to right until you've multiplied all k of those matrices together. The idea of this accelerated power method, the EAPM, is that instead of doing parentheses like this, I can do it like, so I'll write out some p bars first. Let's do 8 of them. So there's 1, 2, 3, 4, 5, 6, 7, 8 of these p bars. And I'm going to group these together, group these together, group these together, and group those together. Then after I do that, group that product together and that product together. And finally, those two products together. And then last would be multiplying by the x down here. And what's cool about doing this is that you notice that, so inside of each of these blue parentheses here, the contents is the same repeated 4 times. So I only have to do this p bar times p bar once, save the results, and I can reuse it 4 different times. And so I'll call that first result Q sub 1. And there's 4 of them, but you only have to compute Q sub 1 once. And then you can reuse it everywhere else. Once you do that, Q1 times Q1, we'll call that Q2. And again, we can reuse the Q2s. We don't have to recompute it over here. And then the very last one, Q2 times Q2, call that Q3. And because we're reusing a lot of these matrix multiplications, it'll turn out that we're able to speed things up in a certain sense. I'm going to scroll up just for a second, but I'll come down here after that. These definitions of the Q sub k, Q1, Q2, and 3, they correspond exactly to this equation 4 right here. It's just, this is the sort of picture version of it. And this is the key idea of the difference between the power method and this accelerated power method is redoing the parentheses so that we can not have to repeat matrix multiplications. Any questions about that? Yeah.
So this is faster than how come it's not used in practice?
So the question is, if this is faster, then how come it's not used in practice? So the next few problems here we're going to go through, we'll actually compute the runtimes or provide formulas for upper bounds on the runtimes in terms of big O notation. And then we'll see what are the situations when the two things are faster than the other and why you might want to use one over the other. So yeah, this part 1 right here, what is the runtime of calculating QK given QK minus 1? Well, the definition up above of QK is equal to QK minus 1 times QK minus 1. Each of these Q sub i's, each of the Q is an n by n matrix. So it's, we can write that the runtime is upper bounded by O of n cubed. There are tighter upper bounds that we could use, but this is the simple one that everybody thinks about in their head when you're doing runtimes of things with matrix multiplications. Hopefully, at this point, it's starting to get like these runtimes a little bit memorized about, yeah, that just two matrices. The reason why this is n cubed, this is n by n, this is n by n. You always take the last one, or the last one and the first one. The two middle ones always have to be equal. So that just is going to be 1 together. So 1n times 1n times 1n gets you n cubed as the runtime. Not only do we have to calculate the Q, there's this like pre-processing or post-processing step that goes on that after we do all the iterations calculating the Q, we have to multiply it by the X. And in this case, I'm also normalizing it by the size of the matrix right here. So we have to consider those runtimes as well. So that's what part 2 is asking. Now it's asking what's the runtime of computing the Y overall in terms of the number of iterations K that you've done. And here that, so we have to compute Q sub capital K. This is a capital K right here. And that's the runtime of each Q sub lowercase k times the number of times we have to do that, which is the uppercase K. And that's going to be equal to O of the uppercase K n cubed. Then there's those post-processing finalization steps. I'm going to just rewrite the formula right here so that we can see it. Yk equals x naught q sub k divided by the L2 norm of x naught q sub k. This product right here. So it's a matrix times a vector. So the output's going to be a vector. It's going to be O of n squared. O of n squared runtime for the matrix vector operation. This, the norm right here. The norm is O of n. This bottom part is a scalar, so we're doing a scalar division as well on this vector that comes out here. That's a scalar division, that blast level 1, linear time O of n for the scalar division. And if you add up all of these runtimes together and simplify, then the top one just dominates, the expense of computing q to the k dominates. And so overall, runtime O of k n cubed, like that. Yes. Which n cubed up here? So this n cubed comes from the fact that qk, the runtime of each individual q sub lowercase k is O of n cubed because it's a matrix product. Matrix products are cubic. And then we're multiplying by k because we do that k times. So it's O of k n cubed. And then the key question is, like we did last time, we need to know how many numbers of iterations do we need to perform in order to get a certain level of accuracy. And so the next page, part 3 right here, this is the thing that we want to bound in this case, that the yk is close to the pi. So the yk is the output of our exponentially accelerated power method. We want to show that that's converging to the actual PageRank vector at a very fast rate and something that is less than or equal to epsilon. I'm not going to at all prove this, but I will just state that this always satisfies this bound right here, that y little k less than or equal to alpha 2 to the k. So I'll set alpha 2 to the k, alpha to the 2 to the k equal to epsilon, and we'll solve for the k value right here. Take the log of both sides, 2 to the k, log alpha equals log epsilon. So 2 to the k equals log epsilon over log alpha. And then one more log, and we get that k equals the log of log epsilon over log alpha. The key thing that's special about this algorithm compared to the power method is that we need many, many fewer iterations in order to achieve the same accuracy. If you recall from the regular power method, so this is the power method in green over here, I'll call it the standard power method. The k was equal to log epsilon over log alpha, like that. And so we need a logarithmic number of iterations to get the same accuracy. So that's where that exponentially accelerated, that the log is taking the log of a number, accelerates it exponentially. Doing the substitution, this value right here into our formula in terms of k, we'll get the final runtime being O of the k value log epsilon over log alpha times n cubed, like that. I'm going to, and this green here is that exponentially accelerated power method. I'll remind us what the standard power method runtime bound that we had was O of log epsilon divided by log alpha times the number of non-zeros in P, or that plus n. There we go. And so here, again, the difference between these two methods is up here. I'm doing a bunch of matrix multiplications, not repeating work that I've already done. So because I'm not repeating work, I get this log factor over here. But because it's matrix multiplications, I get this n cubed factor over here. In the standard power method, we did only matrix vector operations. And in particular, we were able to keep the matrix being sparse the whole time. So we get a much faster term over here in terms of n. We just, in terms of the epsilon, we don't get that extra log factor out here. The vast majority of problems, you don't really need epsilon to be like very accurate at all. Yeah, like something 10 to the minus 3 would be typical. In practice. And so having the exponential acceleration out here is not super helpful because n is extremely large in practice. For Google, in the Deeper Inside PageRank paper, this is like a 20-year-old paper, they mentioned that n's about equal to, I think they said 4 billion, 4 times 10 to the 9th in the paper. More recent announcements from Google have n being about on the order of somewhere between 10 to the 15th and 10 to the 20th. And so even a linear algorithm in a number like this is just really, really slow. If you were to try to do a cubic algorithm in something 10 to the 20, that's just not going to happen. So this exponentially accelerated algorithm will be better if n's like really small, maybe like 10 max, and you really, really care about accuracy for some reason. But that's not really something that happens a lot. So this power method, much more common, much more standard. Question? Question is, are all the logs here base 2? And the answer is that it doesn't actually matter. I think with this big O notation right here, the base of the logarithm ends up just being a constant, and so it gets factored out. But yeah, in my head, if I'm thinking about a base, I'll just pick whatever's convenient, whether it's 2 or E or 10. But it doesn't matter. Good question. Any other questions about the difference between these two algorithms? Chuck?
So the log is n3 being multiplied, so that's like the.
Yeah, I'll be a little bit more careful with the parentheses here. Something like that. Any other questions about differences between these two methods? Yeah. So in terms of, yeah, what does it mean to work better? Both of these two algorithms are going to give you the same results. They both converge to the same PageRank vector. The difference is that they have different runtimes. That's the only difference between them, is their different runtimes. The exponentially accelerated, it has the better runtime if you really, really care about small epsilon. But what it's like a trade-off. There's this inherent trade-off between your epsilon accuracy and your the dimensions of your matrix, the number of nodes in your graph. In order to get really fast convergence on this epsilon accuracy, you have to do the matrix products, and so you get this n cubed right here. For most graphs, though, we would prefer not to do matrix products because they're really slow, and we'd prefer to do matrix vector products. And so if we do that, then we're stuck with this slower epsilon convergence. It's somehow a fundamental trade-off that you can't have both. Because we haven't actually proven that you can't have both, because both of these are upper bounds. And so this one in particular, this n cubed, we know that we can reduce that to like n.3 something is the actual best runtime with matrix multiplication. But yeah, that trade-off is fundamental. You can't escape it. Does that answer your question? So in terms of like, how are you going to be evaluated on this particular knowledge here? The project, you only have to implement this right here. You don't have to implement the exponentially accelerated. On your midterm, there could be questions about, given these particular set of conditions, like maybe n equals 2, and you really want high accuracy, then which algorithm should you choose? There's also in the last packet, there's a third algorithm that I'm asking you to create the runtimes for, and that's the power method. So this power method right here is with a sparse vectors. But I'm asking you to go through the power method runtime with dense vectors and matrices. You'll have to do that on your own, and there could be a question on the midterm saying derive the runtime of the power method on dense matrices and vectors. Good questions. Any other questions? Okay. Then in terms of like material, that's everything that will be on this midterm. Maybe in terms of formatting stuff, I want to talk about this last section of the notes down here. This set of review questions, true, false, open, and exactly what I mean by this, and yeah, how to think about these questions on the midterm. Again, on the midterm, you'll have 10 of these questions. These questions can cover anything that we've talked about in any form. And it's important that you pay careful attention on these questions to the formal definitions of the asymptotic notation. It'll be a really common way for students to miss points on the midterm is by not paying close enough attention to this. So for each of these questions, if the statement is true, then you circle true. If it is false, you circle false. And then if we actually do not know, if nobody in the world knows whether it's true or false, then it is an open question and you circle open. In this case, so we'll start with problem 1 right here. Anytime you see a question like this, whether just asking is something like big O of something else or big omega or a big theta, you know that has to be true or false. It's not going to be open. So if the question is about just like big O notation, the answer is not going to be open. It's just going to be true or false depending on what the statement says. In this case, I think if we work out the division, we'll see that n to the -2 is a lower bound of this thing over here. It's always going to be smaller asymptotically, and so it is in fact true that this function over here is omega of n to the -2. The main situation where this open is going to come up is in the questions about matrix multiplication. Again, we don't actually know what the right runtime, what the optimal runtime of matrix multiplication is. That currently for matrix multiplication, all that we know is that it is omega n squared log n and O of n to the 2.3 something. And the actual full numbers in the set of notes where it talks about matrix multiplication. So using these facts right here, we have to answer these questions down here about the fastest possible algorithm for computing matrix multiplication, matrix products. In this case, we know that matrix multiplication is O of n to the 2.3 something something. But that also means that it's O of n to the any power that's greater than 2.3. So we've been using O of n cubed. That's like the standard thing to do to simplify things. So the standard thing is just to say O of n cubed. And that's okay to do because O of n cubed is bigger than O of n to the 2.3. And you can always substitute something bigger. So O of n to the 4 is bigger than O of n to the 2.3, so that we know that this must be an upper bound on the runtime because this is an upper bound on the runtime. And so this statement is also in fact true. A lot of students will see O to the n to the 4th on a question like this and say, hey, I know that matrix multiplication is faster than n to the 4th, and think that this question is false right here. But if you go back to the definitions of big O, big omega, big theta, this is anything that's bigger than what the actual number is, what the actual formula is. And so n to the 4 is bigger than the formulas that we have, and so it's true. Yes. Yeah, so the question is, here we're talking about the fastest algorithm, and the question is, why is it not omega notation then, if omega notation is a lower bound? And the answer is that no matter what algorithm you're talking about, you can still talk about it in any like omega, O, and theta. Because omega, O, and theta, they are just bounds on some formula. So I'm gonna have space somewhere. Just looking for a spot where there's blank space. I'll do it up here. So quick sort, think about quick sort. Quick sort, or sorry, not quick sort, we want to do merge sort. Merge sort is an example of, and there's many algorithms for sorting that are optimal. There is no better algorithm than merge sort asymptotically for sorting. The runtime of merge sort, we can describe the runtime of merge sort using all three of those big asymptotic big O notations. It is true that the runtime of big sort is omega 1. It is also true that it is omega of n log n. It is also true that it is O of n log n. And it is also true that it is O of n squared or O of 2 to the n. All of these statements about the runtime of merge sort are true. The most important statement about the runtime of merge sort is that it is both omega and O of n log n. When you have a statement that it is both omega and O, then it's the theta of n log n. Yeah, so the asymptotic notations, again, think lower bound, think upper bound. If it's both lower and upper bounded, then it's equal. So down here, this sort of leads us to our problem 3. The fastest algorithm for computing the matrix product AB has runtime theta of n squared log n. When you see the theta, it means that it's both omega and big O. We know for a fact that the runtime of computing the matrix product is omega of n squared log n. So we satisfy the omega. Part. The question is, do we satisfy the O part? And the answer is we actually have no idea. That we know that the runtime, we have an algorithm with runtime into the 2.3, but we don't know if there's an algorithm with runtime, say, into the 2.2 or with n squared log n. We don't know. Nobody knows that. You will be extremely famous if you could come up with an algorithm or prove that there was no algorithm that had that particular runtime. And so this is an example of an open problem. It's a problem that nobody knows whether the answer is true or false. For the, again, in the context of this first midterm, well, we will be seeing many open problems in the future. There are many open problems in data mining and machine learning that nobody knows the answer to. But in the context of this first midterm, the only open problems are problems related to matrix multiplication. And there was one other problem, the matrix chain ordering problem that we talked about in the notes. Those are the only situations where things might possibly be open. Any other situation, the problem cannot be open in terms of this midterm because it will be known to be either true or false. Any questions about the openness of problems?
So it's with matrix runtime, the matrix multiplication runtime, and then matrix chain ordering.
Yes. Those are the only two things that we've talked about that have open problems right now. I don't think I've explicitly stated this yet either, but on your midterm, so there'll be 10 of these questions, and total points 15. If you get a question correct, you get +1 points. Leave a question blank, you get 0 points. Get a question wrong, you get -1 points. So in order to get an A on the midterm exam, one of the things that you have to do is not miss any of the true-false questions, true-false open questions. If you circle the wrong thing on any of these 10 questions, then it guarantees the highest grade you can get is a B. So these seem like simple questions. It's just like one sentence, but it would not be bad to spend a lot of time thinking about those individual sentences and making sure you really understand them. Let's see. So think about number 10 here. Is computing X transpose X faster than computing XX transpose? True, false, open. It's definitely not open. This is true. It happens to involve multiplications here. Vectors. Vectors are a type of matrix, so it could potentially be open maybe, but it is not open. It is either true or false. And this is something that you definitely want to be able to just know off the top of your head. Here, when we have XX transpose, what's the runtime of this going to be? O of n, we're computing just a dot product. So it's just a single for loop that has to go over each of these vectors or the same vector and get that in linear time. Here, the final output is going to be a matrix instead of a vector. And so the runtime, actually here I put an O, will be more precise since they theta. Here, the runtime has to be theta of n squared because the output is a matrix n by n. We have to at least fill in all the entries, and so that takes n squared time. And so this thing on the left is in fact faster. N is in fact faster than n squared. So true is the right answer.
Can we assume that x is an n by 1 vector here? Because it would change it. Like it's not given anywhere in the question, and that would change the answer.
So the question here is, what exactly like is x? The potential options for x. Here, I was assuming that it was an n by 1 vector. Maybe x could be, you might think possibly that it could be, I'll do it in a different color. X could be something like an n by m matrix maybe, or x could be like a scalar 1 by 1. Anytime you see something lowercase bold like this, it's always a vector. So the lowercase bold always a vector. And then here, like, okay, well, maybe this n is like a variable. And so when are we like, okay, maybe I'll just substitute in 1 for that variable. Anytime we're talking about runtimes, we're talking about like asymptotically as these variables go off to infinity. So as n goes off to infinity. And so this is faster than that. It's a great question about technical details, and especially on true and false questions like this, technical details matter. So excellent question. Any other questions on this problem 10? Sure. Yeah, so the question is about number 3 up here. And if we come back over to our exponentially accelerated power method, I was talking about, let's do part 1 right here, where we have 2 matrix multiplications that are n by n matrices. And I wrote right here that the runtime of this is O of n cubed. And if the runtime of this is O of n cubed, then why can we not use this to justify some argument in problem 3? And the answer is that we actually don't know the optimal runtime of this right here. Optimal runtime of that expression is unknown. There is some formula. I mean, it must have a runtime. So there is some f that is the runtime. And all we know about it is that f equals omega n squared log n, and that f equals O of this into the 2.3. And it turns out that here, when I say that this is O of n cubed is bigger than the n to the 2.3. So this is a true statement. Even though we don't know what the optimal runtime of this expression is, we do know that this is a true statement about that optimal runtime. It is not the most precise true statement that can be stated, but it is a true statement. And this is the true statement that is just like convenient for people to use and convenient to remember. It's much easier to remember n to the cubed than all these other details. So this is the thing that people remember. And for practical sizes of n, this is actually like what the runtime is like. You only, like I mentioned this before, this algorithm that has the n to the 2.3 runtime, it's sometimes called the Galactic Algorithm because n has to be larger than like the number of atoms in the universe raised to that same power. in order for this algorithm to become faster than other algorithms. So we still just say that it's n-cubed. Yeah, lots of very subtle arguments going on there, but definitely something that if you don't fully understand that relationship, then you will miss many points on the true-false portion of the midterm. So 100% make sure that you understand those relationships. Let's see, let's find some more good problems for us to work on. Here we go. So this is a little bit related, number 14 right here. So there exists some n by n matrix A such that the number of non-zeros A equals omega of n cubed. First of all, is it possible that this could be an open question? No, it's not talking about multiplication or parenthesization, chain ordering at all, so it can't be open. So now the question is it true or is it false? Anybody have a guess? Shout it out.
False.
False. Why would you say it's false?
Because there's only n by n like elements of the matrix, so you could possibly have n by n zeros.
Yeah, exactly. So the A matrix has size n by n. It's just written right here. And so the total number of elements is n squared. So the number of non-zero elements must be less than or equal to n squared. The number of non-zeros of A less than or equal to n squared. And this is a true statement even without any sort of asymptotic notation right here. But when I say the number of non-zeros of A must be less than or equal to n squared, that means that whatever this function is, whatever its value is right here, it cannot be omega of n cubed, because omega of n cubed, what this implies is that it is at least n cubed. And something that is less than or equal to n squared can never be greater than or equal to n cubed, asymptotically as n goes to infinity. And so that's why it has to be false. So a question like this is testing a lot of different things coming together. It's testing your understanding of the different big O notations. It's testing your understanding of this N and Z notation and some of the basic properties of this N and Z notation. I like true, false, open questions that combine understanding from several different things that way. So expect questions like this that combine many different things. Any questions? Yes.
In the case of the statement saying there exists like 9, 6 is true by pointing out 7 and 1, or I can only set the n by n.
Yes, this is a great question. So the question is here, like, we're looking for a counterexample. And could I create an n equals 1 counterexample? So like the if we had A equals just this one matrix like that. And in this case, it is true that now the number of non-zeros is 1, and 1 is less than or equal to 1 squared, and it's greater than or equal to 1 cubed. But anytime we're talking about the asymptotic notation, we have this asymptotic notation, there's this implicit as n goes to infinity. So you have to have, if you're coming up with a counterexample, your counterexample has to have an infinite or an arbitrary size. It can't have a fixed size.
Cannot have a fixed the A can get but it must be n by specific.
Exactly. You basically have to have a procedure for constructing an A given a size, a particular n size, and it has to hold for everything. Yeah, it's another very excellent question about a subtle point with this asymptotic notation. So I'll say it again, that the asymptotic notation always assumes, so anytime there's like an O, omega, theta, then you're in the regime of n going to infinity. And so because you're in that regime, you can't, your counterexample can't have just a 1-by-1 n equals 1 situation, because this is not an like infinity by infinity matrix. If you were going to come up with a counterexample, then your counterexample would have to work for any arbitrary size matrix, or like infinity by infinity matrix, essentially. If I changed this so that there was no like omega or asymptotic notation here, just like n and z of a is greater than or equal to n cubed, and n and z of a is less than or equal to n squared, then the 1-by-1 example would work. Any other questions about that? Okay, so the first half or so of these are focused more on like the runtime stuff. Then comes the PageRank things. Maybe yeah, I think most of the examples that I have here come from the like counterexamples section of the PageRank notes. Of now you just don't have to find a counterexample. Or you don't have to provide the counterexample. You just write true or false, whether it's true or false. For any time, well, let's see. Yeah, I don't think we have enough time left to properly go over any of these. So I'll leave those for you all to go over on yourselves. And I'll say that the answer key to this true false is actually on GitHub. It's posted in the if you were to come down, so I just gave you the notes3.pdf file. If you look at the text file, so the source code that generated the PDF, scroll down to where the questions are, then each question has a T, F, F, T, whatever the answer is inside of there. And so you can review your work that way. That's it for our class today. Hope you all have fun this weekend working on the projects, studying for the midterm, and see you all Monday or office hours.